Alright guys, how are you? Hope everything is going alright. So here goes our another short video, right, to wrap up chapter 4 on the very last few pages on the probability chapter, counting principles, right? So what's the main purpose of this? Well, we're going to look at different ways to count elements in a set and how many ways to perform certain tasks or to count certain elements depending on a specific situation, right? But we begin first defining what the fundamental counting principle is, right? So the fundamental okay, something's going on. I think it's for okay, yeah, got it. Okay, so the fundamental counting principles, right? So is basically if event A occurs in m possible ways and event B can occur n possible ways, then there are m by n different ways both events can occur, right? And to illustrate this with a simple example, right? So suppose we have the menu of a restaurant, right? In which we have 3 appetizers, 8 main dishes, 4 desserts, and 3 different drinks, right? Of course, menus are way bigger, right? However, for the sake of simplicity and due to the number that we are going to have, well, we're only going to use these small numbers. The question is, so if we assume, of course, one meal as usual is consisting of 1 appetizer, 1 main dish, 1 dessert, and 1 drink, how many different meals can be ordered? All right, so all we do is just multiply the total meals. Just multiply the number of possible appetizers they offer, right? 3 appetizers times 8 main dishes times 4 desserts and 3 drinks, all right? And just multiply that, you should get 288, right? You should get 188. So, let's see. A particular state license plate contains 3 letters A through C followed by 4 digits, right? To avoid the possibility of mistaking one letter for the other, the number 0 and the letter O are not used, right? For this number of plates, the question is how many total plates can be created, right? All right. So this license plate will contain 1, 2, 3, 4, so 3 letters and 4 digits, a total of 7 letters and digits, right? Okay, so the first 3 are letters L, 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 and the others are digits D, 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 and D. Okay, so the alphabet has 26 letters, right? We know that. However, we are not using the O. So we are going to have 25 possible letters, 25 possible letters, 25 possible letters. And the digits from 1 to 9, well, without using the number 0, right? We just have 9 possibilities. So all we do is multiply these numbers 25 times 25 times 25 and then 9 to the 4 if you want to write it using exponents. You can use your calculator and you should get 102,515,625. That many plates, right, are possible. Okay. Example 3, well, it's very similar to example 1. So we have a men's department store selling 3 different suit jackets, right? 6 different shirts, 8 different ties, and 4 different pairs of pants. How many different outcomes or how many different outfits rather consisting of a jacket, a shirt, a tie, and pants, of course using all of them, are possible. So we do the same, total outfits. It's going to be 3 times 6 times 8 times 4. All right. And if we multiply those numbers together, we should get 576. Okay, and that's about it. All right. Okay, what else do we need to, before looking at the permutations and combinations, we need to look at the factorial symbol, right? You may have seen it before. I don't think we went over this when we were in the Maths 96 class, right? However, let's define it. Okay, so n factorial, right? Like it's a number that has an exclamation sign, right? And it's just multiplying that, whatever n is, times itself minus 1, times itself minus 2, times itself minus 3, etc. until you get to 1. Okay, so let's do an example, right? Evaluate 6 factorial, right? And express it in different ways. No, this is not an excited number, right? Like 6, whoa. No, that's not what it means. So every time you see this symbol, you do the following. Multiply 6 times 5 times 4 times 3 times 2 times 1, right? And we stop there, right? And then if we multiply all these numbers, right, we should get 6 times 2. We should get 720. Now, what about expressing it in different forms, in different ways? Well, consider this chunk right here. Okay, let me highlight this. Oops. Okay, let me highlight everything but the 6, right? This is the same as saying, right, 5 factorial, right? Because that's 5 times 4 times 3 times 2 times 1, right? So another way to express this, right, is by saying 6 times 5 factorial. That's another way. Another different way is 6 times 5 times 4 factorial, right? Depending on the needs, right? 6 times 5 times 4 times 3 factorial, and so on. There are different ways. So we're going to need this when we do the permutations and the combinations, which is coming up next. Where to find this on the graphing calculator? All right. So I'm going to go to Math. I'm going to scroll 3 times to the right, and I will reach the prob. Then I will scroll down to number 4. So I'm going to scroll down to, and that's where the factorial symbol is. Okay, let me quit. Let me clear the history, right? Okay, I'm going to do 6 Math. Go to prob. Hit down the 4. Enter. And then click enter again to evaluate. And that's actually the result, 720, just the same way we were getting by hand, right? All right, so let's go back to, let's apply this to permutations and combinations. Okay, what about permutations and combinations, right? So suppose, okay, so suppose you have a set, right? A set comprised by 3 elements, right? And you want to identify unique permutations, right? Choosing 2 elements from the group, right? 2 elements at a time from the group. I don't know, let me give you an example. So suppose you want to form a committee, right? And just to make it simple, let me go to, let's say you want a committee from the set from three people, A, B, and C, right? And you want to come up with a committee of two people, let's say for president and vice president, right? So the question, the thing here in permutation, the order is going to matter, right? Because it's going to matter who's going to be the president, who's going to be the vice president, right? So there's many ways to combine this, right? I can combine A and B, A with C, and B with C, right? Okay, let me write down those combinations, right? Well, permutations rather. AB, it's one. AC is another one. And rather BC, okay? It's going to be the third combination, right? Now, because in this case, for permutation, order matters, so we can have the other order run the other way around. So BA, comma, CA, and CB, okay? So that's the total number of permutations of two elements chosen from a set of three elements. All right. We're going to look at the difference between permutations and combinations soon. Let's go over some examples, but first let's look at the formula. So the formula here involves factorials, right? The number of possible permutations is defined as NPR or P of NR, depending on the notation that you want to use, right? And this is the formula right here. The formula, n factorial divided by n minus r factorial. And we read this as n permute r, right? So let's look at an example, okay? Well, actually, let me go on the side and use the formula, okay? For here I did this by hand, right? Did this by hand. Now let me use the formula. NPR, all right, it's n factorial over n minus r factorial divided n minus r factorial, right? In this case, I'm choosing from a set of three, I'm choosing two, right? And what are we going to do? So that's 3 factorial divided by 3 minus 2 factorial, okay? So I'm going to simplify this. 3 factorial equals 3 minus 2, which is 1 factorial, right? And 3 factorial, that's 3 times 2 times 1 divided by 1 factorial, which is just 1. Okay, so this is going to give us a 6, right? That's a 6. Okay. Didn't we have 6 different permutations, right? See? 6 of them. Of course, this is a very simple case. Now, what if you wanted to do, I don't know, from a group of 7, A, B, C, D, E, F, G, right? What if you wanted to do that? Okay. And then you want to form permutations of 3 elements. You are not going to combine 3 elements at a time, right? Like A, B, C, like A, B, D, right? Like A, B, E, and then A, B, F, A, B, G. Okay, I'm already getting tired of counting them all, right? In this case, that's why we have this permutation formula to find how many permutations of 3 elements from a set of 6, right? Or rather 7, not 6, but rather 7. Did I say 7? Yes, 7. Okay, we're going to look at more examples, right? Okay, so let's see. Let's look at the first example. So a salesperson is responsible for taking care of 9 stores, right? Of whatever company. How many different ways can she schedule visits with 5 stores in a certain week? All right. Well, so in this case, why order matters, right? Because she's going to go from store to store, right? So let's see how it works. Okay. Let's write down the formula first. NPR equals n factorial divided by n minus r factorial. Okay. And in this case, from 9 stores, she wants to schedule to visit 5 stores, right? That is, we are doing from 9 stores, we permute groups of 5, right? So that's going to be 9 factorial divided by 9 minus 5 factorial. Let's simplify this. That's 9 factorial divided by 4 factorial. Let's simplify the factorials. Remember the different ways to simplify factorials. So I'm going to do 9 times 8. I'm not going to go all the way 1 times 7 times 6 times 5 times, instead of writing 4, 3, 2, 1, I'm going to write 4 factorial. And I'm going to cancel it out with this 4 factorial, which we can do right here, right? So we are left with 9 times 8 times 7 times 6 times 5, which equals 15,120 ways to schedule visits, right? From the 9 stores to choose, actually to permute visit of 5 in a week, right? Okay. So it seems like it might be a little bit tedious to write this down, right? So the good news is that we have a calculator command, right, to evaluate permutations. And I'm going to use that on the following examples, right? So calculate the number of ways 8 swimmers can place first, second, or third. Okay, why is this a permutation? Because in this case, order matters. It matters who's going to be the first place, the second place, and the third place. It's not like oh, it doesn't matter as long as there's a first, second, and third. That's fine. No, it turns out that it does matter actually, right? So that's why we permute. We're going to do the permutation in this case from 8 permute 3. Let's just use the graphing calculator. Okay, let me switch the window to Smart View. Okay, let me clear the history here. Okay, I'm gonna go math again. Prob, that's 3 times to the right. And then, what am I gonna do? I'm going to scroll down to number 2. That's scrolling down only once, and click enter. When you see the permutation symbol, so all we do is put the number 8, the 8 swimmers, the number of swimmers in the tournament, and the number of winners, first, second, and third, right? And then just click enter. Okay, that is 336, right? So 336 is the answer to this. Okay. Again, you can use that on the application if you installed it on your laptop, or if you downloaded the calculator software on your cell phone. All right. Okay, let's look at example 3. A combination log has a total of 40 numbers on its face and will unlock given that the proper 3-number sequence is input on the system, right? How many unique combinations? And be careful, not because you read, the word combination, this is going to be a combination problem. Okay, again, we're going to look at the difference between permutations and combinations on the next section. Okay, so in this case, why order matters? Because it's a combination lock, right? It's always a password, right? So it's only going to be from a very unique sequence of numbers or letters, right? In this case, it's 40 numbers, right? And the one that is going to work and unlock the lock, right? So in this case, we are going to permute, right? From 40 numbers, we are going to permute. So in this case, notice it is a 3-number sequence, right? 40 permute 3. And let's just use the calculator, right? Okay, so you might want to, let me clear this again. Okay, let me go math, prob, go down to NPR, click enter. Wait a minute, it didn't work. Oh, okay, I can copy it. And I'm gonna do 40 and 3 as well, right? And I get 59,280 possible permutations of numbers, right? 59,280, okay? Example 4 is going to be very similar to the one we did on example 2, right? So the number, so there is this movie festival, right, in which there were 18 entries, right? 18 films. So a committee, right, or rather the judges are going to choose a first, second, and third place, right? So all we do is from the 18 films, we are going to choose 3 places, first, second, and 3. Okay, so let's see. Clear. I'm going to use math, prob, NPR, and that's going to be 8 from 18. We'll do 3 of them, and we get 4,896. 4,896. All right, final answer. So a lot of what we're going to be doing for the rest of the semester, for the rest of the class, is a lot of calculator, right? Of course, I will be doing more often than not, like at least one example by hand, and then show you the difference and show you how to do it on the calculator, okay? So, special permutations rule. Okay, the number of possible permutations of an object among themselves is n factorial. All right. So this is telling us, right? Instead of having, for example, a permutation of 3 permutations of 3 elements from 18 from a set of 6 elements, right? We are going to make permutations of 6 elements from the total of themselves, right? That is, in other words, n permute n, right? Okay, so n permute n will be n factorial divided by n minus, it would be r, right? But this was replaced. Okay, let me erase this n and this r. This used to be an r. It's getting replaced with an n. So that's n factorial. So n factorial divided by 0 factorial. By definition, 0 factorial equals 1. I didn't mention that before, right? So n factorial equals 1. And n factorial is the final answer, right? Which is what we were getting here. Okay, let me illustrate the picture. Okay. What if I have 5 students, for example, and the 5 of them are taking an exam, all right? And of course, they're competing for, okay, A, B, C, D, and E, right? The 5 students, right? A, B, C, and D. And they're competing for a first, second, third, fourth, and fifth place, right? Because in this case, order matters, right? If A, okay, how many possibilities can A wins? Okay, for example, let's say A wins the first place, right? So the first place is already taken, right? The first place is already taken, so nobody else can take the fifth place anymore, right? So now, once A gets the fifth place, student B has the chance of scoring from the first place through the fourth place only. That's only 4 possibilities, right? So A and B are done. Now the competition is between C, D, and E, okay? If the fifth and the fourth place are already taken, then C only has 3 possibilities to score the first, the second, or the third, right? And likewise now, there's 2 students remaining, so they are now fighting for the first and the second place. So D has 2 possibilities and E is the winner with only 1 possibility, okay? If we do that, we get 5 times 4 times 3 times 1. Then 2 times 1, isn't that the same as 5 factorial, whatever that is, right? 24, I think that's 24 times 5. I believe it's 120. I don't know. Okay, so that's the idea of permutation of object among itself, right? And how do we apply that here? Okay, let's look at one example. The total number of ways 8 people can be seated at a table has 8 seats. All right, so let's find. Okay, so let me draw a table here. Okay, let me draw a table real quick. And this is going to have 1, 2, 3, 4, 5, 6, 7, 8 chairs, right? Okay, so whoever gets first to the meeting, right, to the restaurant or whatever, I don't know, maybe a Thanksgiving dinner or a Christmas dinner, whoever gets first gets to choose, has 8 possibilities to choose. Whoever gets second to the place has 7 possibilities to choose, right? Whoever gets next 6 and then 5 and then 4, etc., right? 3, 2, and 1. So we're basically multiplying 8 times 7 times 6 times 5 times 4 times 3 times 1, right? That's what we're doing. Ultimately, we're just doing n factorial, which in this case is 8 factorial. And using the calculator, let's see. And this is 8 math prob number 4, 8 factorial, and then enter. So we get 40,320. 40. Oh, I think I got it here. Okay. I think I got it. Okay, let me copy that again. Yes, 4320. All right. Okay. Example 2. A student has 10 books to arrange on a shelf of a bookcase. How many ways can those 10 books be arranged? The reason why this is 10 factorial is because, well, when you put the first book, right? The first book you choose to put it on the bookshelf will have 10 different possibilities, right? And then the 9th book will have 9 many ways, and then 8 many ways, and then 7 many ways, and then so on and so forth. So that's why in this case it's 10 factorial, right? Which in this case, if you use the calculator, you should get, let me use my calculator too, we get, oh, it's a big number, 3,628,800 ways, right? Now, example 3 might be a little bit more tricky, right? Okay, how many different ways can 5 people, A, B, C, D, and E, sit in a row at a movie theater with the condition that A and B have to be together, right? Okay. Now, let's see. Okay, the fact that A and B have to sit together. Well, number one, we have 5 people, right? We have A, B, C, D, and E, right? So we will look at 5, 4, 3, 2, 1 ways. However, in this case, we need to consider the fact that A and B must sit together, so we can place them in one place to make sure they are together, right? Now, A, B together, there are 4 possibilities, and then 3, and then 2, and then 1. However, because in permutations order matters, right? There's one possibility of A, B being together by sitting A and B first, or the other possibility by having B and A then together, right? So these two, C and D, that looks like a B, and then E. And that's the same 4 times 3 times 2 times 1. Okay, so 4 times 3 times 2 times 1, that's basically 24 plus 24, which is 48. All right, that's another example. Okay, what about the another type of permutations when we have repetition of elements, right? So we are going to use this formula right here, right? And in this case we are going to have elements, right? Okay, let me write a set right here, and an element that has repeated like 3 greens, right? 4 oranges, and use a different color. What else? Purple. 1, 2, 3, 4, 5, 6 purple, right? We have repetitions of the same element, right? So a very typical example that has to deal with repetitions is, for example, how many ways can we arrange the letters from the word Mississippi? Okay, let me write it down on the side. Okay, CP. All right, another way to permute this is M, S, I, S, I, S, S, I, P, P, I, right? But I mean, this S is repeated here. What about the S's here? What if it's the S from here? How do we make a difference? There's no way we can make a distinction with which S is which, right? In fact, it will be a huge number of permutations, right? So let me show you how to get this. Okay. So number one, let's list the different repetitions that we have. So I'm going to call N1. I'm going to label N1 the number of repeated I's, right? Because notice the one of the repeated letters is the letter I in the word Mississippi. N equals 2 will be the letter S, because we see the letter S is repeated. And I also see the letter P to be repeated, right? And let's write down how many of each. Okay, so we have a total of 4 I's, 4 S's, and 2 P's, right? And N, which is the grand total of elements, in this case the number of letters, which is a total of 11 letters, right? So I'm going to adapt this formula right here, right, to our problem. Okay. And I'm going to say permutation. I'm going to permute from 11 elements with 4 i's, 4 s's, and 2 p's, right? I'm going to write n factorial, which is 11 factorial, divided by the first repetition factorial, 4 factorial, times 4 factorial, times 2 factorial, right? I'm going to give you the answer to this. This is going to be 34,650. I'm going to show you how to use the calculator for this, right? Because I'm pretty sure there could be a lot of room for mistakes when using the calculator. I'll show you how. Okay, so I'm gonna do one at a time. Okay, this might take a good minute. Okay, so I'm gonna type 11 and I'm gonna go math prob and scroll down to number 4 to reach the factorial symbol. Okay, I'm going to divide by, and when you divide, make sure to open parentheses and then close it at the end to make sure everything ends in the denominator, right? So this is going to be 4 factorial. Let me get the factorial symbol times another 4 factorial, and then times a 2 factorial. And okay, and close parentheses. And that's our final answer. The room for mistake is this, guys. Let me copy it down. The room for mistake is by not putting these parentheses, right? That's most likely what one would do in the first place. And look at the answer. It's a totally different answer. You see on the screen? Okay. So let's use the first one, not the second one. So okay, here's the answer. There's a bag of 12 Skittles in it. There are 3 red, 5 blue, and 4 green. Okay, a person is going to select one at a time and then line them up, right? So let me give you the picture for this, right? In the set, in the bag of Skittles, there are 3 red, 5 blue, and 4 green, right? Okay, I think I went one. Okay, so we are going to line them up one at a time. So one way to line them up is, I don't know, maybe 1 green, and then a blue, and then another green, and then a red, right? And then another red, and then another green, and then another blue, and then another green, and I ran out of greens, and I have 2 more blue ones, 1 blue, or rather 3, and then another, okay, this is red, another red, I ran out of red ones, and then did I run out of green? I ran out of green, I still have 3 more blue ones. I mean blue, blue, and blue, right? So, oh no, one less. Now, another possibility is, well, maybe getting the 3 red first, and then 1 green, right? Or rather 2 greens, for example, right? And then 3 blue, the other 2 greens, right? And then the other 2 blues, right? Okay, so that's 5 and okay. Another possibility, right? And we can write many possibilities. Do we have time to count them all by exhaustion? No, we are going to use the permutations with repetitions formula, right? In which This is our n. 3 red is n equals 1, 5 blue is n equals 2, 4 green is n equals 3, and 12, the total number of Skittles, which is 12, is the n. Okay, so we are going to permute 12 with 3 repetitions, 5 repetitions, and 4 repetitions of elements. So 12 factorial divided by 3 factorial times 5 factorial and 4 factorial. Okay, I will give you the answer to this. Oh, I don't have the answer to this. Okay, let me go back to the calculator window. Okay, you might want to copy this expression and change the numbers. So instead of 11 factorial in the numerator, change it for a 2. You are going to have a 3 factorial, 5 factorial. Whoops, this is supposed to be a 5. Okay, let me delete this. Oh, come on. Okay, let me copy it again. Okay, so 12 factorial, 3 factorial, 5 factorial, and 4 factorial. And in fact, I copied the wrong one. Did you notice that? Okay, we should use the one with parentheses, by the way. So 12 factorial, 3, 5, and 4. Final answer, 27,720. Okay, 27,720. Do you want to try this 27,720 possibilities? Thanks, but no thanks. That's going to be like a huge task. All right, so we already gone over all the possible different ways to do permutations depending on the case. Now we're going to do combinations, okay? Combinations are going to be in a similar way as in permutations, right? So we are going to consider, right, the same set of elements, and we are going to consider 2 from the set of 3, right? But in this case, unlike permutations, for combinations in summary, order doesn't matter. All right, order doesn't matter. Okay, so let me consider the same set I showed you earlier, A, B, and C, right? Comprised by these 3 elements. All right, so one element, okay, we can combine A with B, A with C, and B with C. Let's write them down. All right, so AB, AC, and BC. When we did the permutations, we included the BA, the CA, and the CB, right? In this case, we are not going to consider this other orders, right? Because order doesn't matter. So in this case, when we have combination, order doesn't matter. So AC is, AB is the same as saying BA, right? AC is the same as saying CA, and CB is the same as saying BC, right? Order doesn't matter. Like, under which situation? Okay, let's say, okay, suppose you go get ice cream. You go to the ice cream place, right? And they have 3 flavors. So if you don't mind having one flavor first and then the other, well, if you don't mind, so a combination, the possible combinations is 3, right? However, if you go to the ice cream place, right, and you're kind of picky, oh no, I want certain flavor first and then the other, then you will be talking about permutations, and in that case, you consider the 6 total of permutations, not just 3. So order matters on permutation, or doesn't matter in combinations. The formula is going to look similar to that of the permutation. However, the new thing is just this r factorial in the denominator, and the way we read it is n choose r. And we are going to look at these combinations later on when we look at probability distributions, right? And we are going to use this symbol nr with parentheses, which is like the binomial coefficients. You may have seen it in your pre-calculus algebra or algebra class. Right, so let's see the difference with an example. So a young woman bought 7 books to read on a vacation, but only has time to read 3 of them. How many ways can she choose 3 of the 7 books to bring with her, right? So yeah, she doesn't have enough space to carry the 7 books, so she's going to select 3 books, right? In this case, we are going to consider that the books are not related to one another. It's not like she has to read the first one, the second one, then the third one, right? Like, I don't know, like a Twilight Saga or like Star Wars saga books, right? That have some continuity, right? So in this case, I don't know, it's a magazine and then a novel and then, I don't know, a textbook maybe, so they don't have connection to one another. So order is not going to matter. So from her set of 7 books, she will choose 3 of them. So let's use notation. And let's do one by hand, and then I'll show you how to use it, how to do it on the graphing calculator. 7 factorial divided by 7 minus 3 factorial times 3 factorial, right? The 3 factorial remains in the denominator. Okay, let me simplify 7 times 5 times 6. Wait a minute, no, that's not the correct answer. 7 times 6 times 5 times 4. I'm going to keep it in 4 factorial because I'm going to have this guy right here to be 4 factorial times 3 factorial. And we can simplify the factorials. 4 factorial with 4 factorial. Okay, so 7 times 6 times 5. We know 3 factorial is 6, right? So this will be divided by 6. And we can cancel this 6's and we are left with 7 times 5, which equals 35. So she can choose 3 books out of a list of 7 in 35 ways. Let's do this in the calculator. Okay, I'm going to show you. It's going to be essentially the same steps we did before, right? So now let's go math, prob, and just scroll down to number 3. That's the n choose r. In this case, out of 7, we choose 3. Final answer, 35. And there it is. Okay. All right. So let's do another one. Calculate the number of unique 4-person groups that can be formed by selecting from 8 eligible candidates, right? So there's a committee of 4 people, right? Being selected from 8 potential candidates, right? So out of 8, we are going to choose 4 of them. Okay, we already did the selecting people, right, on the permutations, but in this case, why in this case it's a combination and not a permutation? Because on the other problems we did with permutations, we were looking for a president, vice president, or secretary, right? Or first, second, and third place, right? Depending on the situation. In this case, they're just telling us to do groups of 4. And they're not telling us that one particular person is going to be president, vice president, secretary 1, and secretary 2, right? They're not telling us anything, just the possible ways to do groups of 4. And that's about it, okay? So if we use a calculator, 8 choose 4, we get 7. There are 70 ways to get groups of 4 out of 8 people, right? Let's see. How many ways can you organize if you have a class of 25 students, like our class, into groups of 5? Okay, so that's 25, choose 5. Okay, use the calculator to get no other than 53,130. Okay. 10 people attend to a party, right? And if each people shakes hands, how many total handshakes will occur, right? Well, in this case, why is this a combination again and not a permutation? Because when you go to a party or you go to a room or whatever, right? You're typically going to greet whoever is close to you, right? So you're not going to go to the meeting, and on your way to the meeting, you're going to think, no, I'm going to say hi first to John, and then I'm going to say hi to Mike, and then to Robert, and then to work, right? You don't think of that, right? You're not setting up an order, right? Unless you want to do that, well, maybe it works, but in this case, we are going to assume that people is just going to shake hands with each other, right? And in whatever order, regardless of the order, right? Now, out of 10 people, right? We are going to choose how many? Well, in this case, we choose 2 because we are going to assume that 2 people shake hands with each other at the same time, right? You're not going to shake hands with someone with the right hand and the left hand at the same time, right? That's not how you greet your friends or how you greet people at a formal meeting, right? So that's why 2 people shaking hands at a time out of 10. So 10 choose 2, we get 45. Okay, and just to wrap up this chapter, let's see the difference between combinations and permutations. So we have a teacher that has 30 students in her class and needs 5 of them to go to her office to pick up texts or other materials, right? So out of 30, she needs 5. For example, a teacher has also 30 students. I'd say 35, she's supposed to be 30. And she needs 3 students, one to be the president of the class, the other one to be the vice president, and the third one to be the secretary, right? So she's going to need 3 of them. One of them is going to be a permutation, the other one is going to be a combination. I may claim the first one it's a combination and the second one it's a permutation. Why? Because order doesn't matter here. And for permutation, in this case, order matters. Order. So when the teacher asks 5 students, she's not going to say, oh, I want you to exit the room first and then you. No, it doesn't matter. She just needs 5 random students, right? That's all she needs. However, on the second case in which we do the permutations, we use the permutation because it will matter who's going to be the president. It is going to matter who the vice president is going to be, and it's going to matter who the secretary is, right? It's not like, oh, okay, I just need 3 people and just whoever you want to be, okay, there you go. No, that's not how it works. Imagine if the elections were that way. No, so that's not how it works. And if you use the calculator, 142,506 ways to send 5 students, and 142, oh wait a minute, not 142, 30 permute 3 will be 24,360. Okay, and that's about it for this. This is where we wrap up the chapter. There's one page, there's page 33. However, I'm gonna skip that because we're gonna get more more in detail when we look at the next chapter. Actually, you'll see what I mean. When we will go back to this page when we look at that. Okay, so in the meantime, that's the end of the chapter, and we may talk about an exam, and I will let you know about the rest of the homework in the meantime. See you on the next video. Okay, bye bye.